Brought to you by MuleSoft, provider of the industry-leading AnyPoint platform for APIs.
Okay, so today I want to tell you why I think that we'll soon see an integrated future, as I call it, and I will also tell you how you can optimize for that future. But first we should probably talk about why we're even talking about those things. I mean, it isn't that long ago, well, 20 years or something like that sounds like an eternity, but there used really to be a time where data was actually not available at all. It was a scarce resource. So even if you knew that the data was available somewhere, if it was available in your organization somewhere, most of the time you didn't have access. Probably your workstation was running on a different network stack than the server where the data was stored, so you had to find some person that finally could give you access. And that was basically what triggered the creation of the World Wide Web in the first place. So when Tim Berners-Lee wrote this proposal for an information management system that built the base for the World Wide Web as we all know it, he had really that in mind. He really wanted to have access to data, to documents, regardless of where they are stored. So he wanted to have a system which has kind of a global view of all the available documents, primarily in the traditional web. Luckily, at that time, Tim Berners-Lee manager found that proposal vague but exciting. It's a bit small here, but that's what he wrote in the proposal, and he allowed him to work on that as a side project. And within not even a year, I think Tim had all the basic components in place. He wrote the first version of a browser. He wrote the first specifications for URLs, the web addresses, and also the first version of HTML. And I think the rest is history. I mean, we now have more than 1 billion websites out there, more than 60 trillion web pages. And that's, by the way, a quite conservative estimate. So those 60 trillion, for example, are just the websites the web pages that Google is able to index. So everything that sits behind the login wall or that isn't available publicly isn't included in that number. So probably it is actually quite a bit higher. But that is all kind of a document-based web. So you would have to go retrieve a document and then kind of extract the data, and that's mostly a manual process to make sense or to further use that, leverage that information that is available there. In order to kind of avoid that double work, because the server has a database already, it transforms it to an HTML document, and then the consumer has to kind of do the reverse process. Web APIs were created, basically. So that was the main reason. People wanted to exchange data directly. They wanted to have direct access to the data to avoid those conversions back and forth. And I mean, we've seen tremendous growth in that space. So people really like that. But unfortunately, using those web APIs is still more challenging than it should be. So it's not like on the document-based web where, just a friend sends you a URL, a link to some website, you plug it in your browser, and then you look it up and start interact with that website. Or if you don't know the URL, you just Google it and you're there in a couple of clicks. If you want to use a web API, the first step you normally have to do is you have to go find the documentation, read that documentation, probably you have to download an SDK, then you have to integrate that, you have to kind of build a small application to have a user interface or some other interface to the data, and then you can start to do the actual work, to do the interesting work. And whenever the API changes, even just slightly, you have to do that step over again. So your client will break, you have to download a new version of the SDK, you have to reread the documentation, and all that stuff. And basically, that sucks, I would say. I mean, it is, of course, it works in a sense if you just interact with a small number of web APIs. If you have just 1 or 2 web APIs, it's not that bad. But if you look at it from a system perspective, it's really not that great. So if you're building an application and you interact with a couple of web APIs, then you also need a couple of SDKs. So it scales linearly. The more web APIs you add, the more SDKs, the more dependencies you have. Those dependencies increase your code base. They introduce dependencies, of course, which may or may not matter to you, but it's a lot of third-party code, untrusted code, so it could contain bugs, memory leaks, security vulnerabilities, or in the worst case, even backdoors. That code typically runs with quite a few permissions, so it obviously needs to have network access. So you really open up your systems, and there is not really kind of a practical way around it. So the best thing you can do is, of course, implement everything yourself by hand, but then you spend like months just to get started. So that's not a viable option either. But if we look at this, then it still kind of scales linearly. The more APIs you add, the more complexity you get. But if you look at it from really like from the web's point of view, if you say that each of those APIs also needs to talk to other APIs, then complexity really quickly gets out of control. Then you have, for n APIs, you have roughly n square of those integration points. And that is simply not manageable anymore. So if you have 10 APIs, we're talking about 45 integrations. If you have 100, we're already talking about 5,000. And if you just have 1,000 APIs, and that's a really small number on the web, we're talking about 500 million of those integrations. So that certainly doesn't scale. So we need to find a solution to that, and that's what kind of triggered my work and my interest in this thing. And if you think a bit more about it, it's actually exactly the same problem that Tim Berners-Lee wanted to solve when he created the web in the first place. So we had exactly the same situation 20, 30 years ago where the data was there, but we didn't have access because everyone was talking a different language. And the solution that he chose for the web actually works as well for web APIs. And the solution is quite simple. So instead of talking in different languages, we introduce one central standard or a set of standards. It doesn't really matter. The thing that matters is that it is centralistic. So whereas the whole web is kind of a decentralized system, the standards are always centralized. And if you then just program against that a single standard, you don't need n SDKs anymore. We are not talking about n square integrations anymore. We are just one standard, one SDK, and quite a few, and much less integrations, of course. So every web API just has to map its internal data model, whatever, to that standard, and that's all. And everyone speaks the same language, and that way we kind of achieve interoperability, and the whole system starts to scale again. So basically, it's the same as we had with the web. We have one standard for addressing things. We have URLs. We have kind of one language, which is HTML on the document-based web, and HTTP, which is the transfer protocol. Now, there are, of course, a lot of people trying that, but I think the most promising solution to this problem is linked data. And the reason why I think it is so promising is because even though a lot of people don't believe it, but it's actually extremely trivial, and it is built on the basic ideas that the web is built on. And funnily enough, it's quite easy to explain it if we go back to the very first proposal for the web. So if we look at this diagram a bit more closely, we have actually the perfect explanation of linked data. So already in that first proposal, Tim Berners-Lee not only included documents, but also other things like abstract concepts such as hypermedia, hypertext, even real-world things like persons or organizations. And we can do the same with linked data. So we can express information about all those things in a generic way. And the way we do that is for every concept we have, we give that concept a resource. So a resource represents a concept, and the resource is identified with a URL. And of course, just as in a document-based web, we can interlink those resources. So we can, for example, connect two resources together. That link is typed, so it is labeled with a certain relationship. So in this case, we can express that a proposal describes the CERN in this case here. So effectively, we kind of build up a little language. We can also look at this like a sentence. Sorry. So we have a subject, the thing we are talking about, the predicate or property, which is probably the easier term, and an object. And that way we really have a language. And the trick behind that is to make that language unambiguous. To use terms, not natural language, but some constructs which have a well-defined meaning so that machines can also make sense of it. Just to revisit that, so on the web, those identifiers that we want to use instead of natural language are URLs, and we can use them in all three components of such a triple or such a sentence. So we use URLs for everything. And the nice property of URLs is that if you don't know what a URL is, you just you put it in your browser and look it up. So you can really look up the definition of those identifiers if you encounter them and don't recognize them yet. So unlike, so if you would use primary keys in a database table, for example, that makes sense for you in your system. But if I send you, 33, if I send you just that, nobody else can make sense of it. I have to send you a whole lot of context so that another party can also make sense of it. But if I send you a URL and you don't know what it is, then you just look it up because it is already like a global valid identifier by definition. Of course, URLs are not always the only option. So in some cases, you really need strings, for example, in the object position. If I'm talking about, I don't know, a product description, it doesn't make sense to have the object to be a URL as well. Or for things like prices, I also have typed values. But that's really it. That's the complete data model. And if you haven't recognized it yet, that's actually RDF in a slide. So actually, RDF, the data model, is that simple. Even though it really looks complex, people are scared of RDF. Most people are scared of it because of RDF XML, which for a long time was the only serialization format. And it's a really ugly serialization format. You really can't read it. So you can't understand what the data is about. But if you just look at the data model, then it's really that simple. So you just have sentences, basically, and you try to identify everything with URLs so that you can look those things up if you don't recognize them yet. And just to make this a bit more concrete, so if we, for example, would like to describe me as a person, I could mint a URL for myself. So I could use some URL from my domain, a subdomain, and then I could express that my first name is Marcus. Now, as you see in the predicate position, I didn't just made up a random URL, but I used schema.org in this case. And the reason why I used schema.org is because we would like to use a shared language, a language which other people speak as well. So basically, we would like to have a shared vocabulary. And schema.org is just that, a shared vocabulary. So it is a set of URLs which have a well-defined meaning. And one of the concepts that they happen to define is the concept of a first name. And the thing that makes schema.org so interesting is that it was created and is thus, of course, also understood by the 4 major search engine providers. So whenever you use schema.org somewhere, Google, Microsoft, Yahoo, Yandex, they will all immediately understand what you're talking about. So you don't have to, sign up for something or do something special. They really just get it, kind of. And of course, it's also not just them. There are a whole lot of companies and applications that support schema.org already. And just to give you an idea of how such a definition looks like, here's the definition of that property that we used before, so schema.org/given name. And it's kind of obvious, like a dictionary. It also tells you that the values are to be expected of the type text and that those properties appear on the type person. So even if I didn't express explicitly that I was talking about the person, you could kind of infer that I was talking about the person by just that definition. And obviously that definition is also available as machine-readable data. So why did search engines create something like that? I mean, on one hand, it's kind of obvious. They want to understand the data. And they could, of course, also do something like natural language processing or things like that, but that quickly gets very expensive and complex, and it's also very brittle. So they needed something a bit more reliable and something which is quite simple and helps them to realize a couple of use cases which would otherwise be impossible. So for example, if you Google for a recipe, in this case here I Googled for white chocolate cheesecake, we'll see that Google returns a nice list of results. In this case, the results are especially interesting because we not only get like the traditional title and the small text snippet, but as we see in the second example here, also a quite relevant picture. So it's not a random picture, like really deep picture which represents that recipe, and a bit of structured information. I will zoom in a bit for you. So we see that Google also displays, for example, the ratings that this recipe got. And this is not a rating that people did on google.com, but really on that website. It also shows the preparation time and the calories of that recipe. And that's something that you would normally realize with a web API. So normally you would have your website, that recipe would have some kind of ID, then you extract that ID, put it in the API somewhere, and then you get back that structured data. But even for Google, with their thousands of engineers, that was too expensive, so they really needed another solution. And the way this works is quite simple, actually. So if you look at that website, we'll see, of course, that the same data is there. So we see the ratings, 86 ratings. We also see the calories somewhere up there, and the preparation time. And the preparation time is actually quite interesting here because it is actually not 6 hours, 25 minutes, but 25 minutes plus 6 hours. And those two things are in different paragraphs, so natural language processing would be quite tricky in such a case. And similarly, the nutrition table down there, it has very little context, so natural language wouldn't work there either. And if you look at that a bit more closely, if you look at the source code of that table down there, we'll see that actually it is not even a table. So it's a div block and a definition list. But as you already see in that snippet, there is some markup in there which uses schema.org. So in this case here, they say that this div block here represents something which is of type schema.org nutrition information. And that tells Google what it can expect in that block. And of course it continues, so also the properties of that thing, of that nutrition information are marked up. So we have a property calories with a value of 667. And in case you wonder why there's just calories and not schema.org calories, that's just because that format, microdata, allows you to abbreviate that. In reality, it's really schema.org calories. And that way, Google can really reliably extract that information and use it to render their search results more nicely. Of course, sure. Primarily the 4 search engine providers, but it's kind of an open effort, so you can also propose something yourself, and it's a collaboration, basically. And, well, that's what Google is doing, and as I said before, it's actually quite trivial, so it's not just, big companies that can leverage that data anymore, or, normally the way those things work is if you are a big company, you have some partnerships and then you kind of have a competitive advantage. But this is an open system, so also small players like Pinterest, which is still a comparably small startup, can leverage that data. And if you look at it, at this pin of this recipe here, you see that they are actually extracting even more information and using even more information. So not only do they extract the preparation time, but also all the ingredients. And that, of course, enhances the user experience on their site quite a bit. Users get much nicer pins, there's more interaction on the site, more information on the site. And of course, it also benefits Pinterest again, because they have more content, Google will see more content, so they will rank better. And that's actually quite an important aspect of it. So also the publisher itself of that data benefits from it. So the New York Times, for example, stated in their recently leaked innovation report that by just adding a little bit of structured information to their recipes, the visits to their recipes from search engines increased by 52%. And that's quite a bit. I mean, that's real money. It's really a value that you can attach some monetary value to it. So it's kind of a win-win situation. The publisher gets more traffic. Google is able to leverage the data to show more relevant search results. Pinterest gets a more interesting user experience, etc. So kind of everyone benefits from that shared data and from the fact that everyone has access to the data without having to coordinate things and read documentation and all that stuff. So that has been a huge success for Schema.org, for the web in general. These days, 20% of all web pages out there are annotated this way. And if you compare that number, if you remember, I said there are 1 billion websites out there, 20% is 200 million websites. If you compare this number with the 12,000 web APIs that we have in Programmable Web's API directory, I think it's not hard to recognize how big this already is. And I think it definitely makes sense to look at it also from an web API perspective, because it has a lot of quite unique advantages and features that we could leverage. But of course, I mean, I'm not proposing that we switch all our JSON-based web APIs to web APIs that, you know, serve HTML, semantically marked up HTML. I know a few people do that. They advocate such an approach, but I'm not really a big fan of that, because in most cases, you are not interested like in the visual representation. You're just interested in the structured data, the raw data in there. And thus, something like JSON is a much better fit. And to kind of bring all those features, that goodness, that scalability to web APIs, so we started to work on that. We started to try to kind of bring those principles to the world of web APIs. And since January this year, we now have an official W3C standard. It's called JSON-LD, and it's just that. So it's simply speaking a set of conventions which allows you to serialize such data in a JSON-based format, in a quite idiomatic JSON-based format. So if we look at that example, we can translate it to JSON-LD quite easily. It's actually quite straightforward. So we just have a JSON document as usual. We have a couple of key value pairs, so calories, 667, protein content, 9 grams. And you can choose the property names as you want. It doesn't matter what you choose here. The trick lies in the context which we add. So we add enough context for a machine to make sense of that data. And the context is actually, simply speaking, nothing else than a mapping from those property names here, for example, to Schema.org. And that way they become meaningful. They get a sense, the machine is able to understand them, to interpret them. And of course, in this case here, we would have a lot of those mappings, and they would basically all look the same. So we can even simplify that here. So we would just need to say, in this case here, we are using the vocabulary Schema.org, and that's it. And that way, a machine really is able to extract that data. It will recognize we're talking about nutritional information here. We are not talking about persons or anything else. And of course, I can that way reuse a lot of code across projects, across web APIs. I don't have to adapt to every single web API anymore. Now, the only thing that's kind of missing here, and that's missing in Schema.org, is that it's kind of a static description. So you have a description of what the recipe is, what the nutritional information of a specific recipe is, etc. But if you're building a web API, you typically want to allow users to interact with that data. You want to allow them to add new recipes or modify existing recipes, etc. So, for example, if you would build a web API, you would quite likely have a collection of recipes. So normally you would do a get, for example, example.com/recipes. You would get back a JSON document. It would be a collection. So this is a JSON-LD document. It would also have a couple of members and probably a couple of other properties. And now the question is, how can you add a new recipe to that collection? Now, typically, you would now need to go and read some API documentation and then hard code that knowledge in your client, or download an SDK which does that for you. to change that, we created a new vocabulary to kind of bring that goodness or bring that understanding to machines as well, so that they can read the documentation for us, so that we don't have to do it. And that's called Hydra. And Hydra basically allows you to complete the description of that resource, of the recipes resource here, and it allows you to tell the machine what operations this resource supports. In this case, there is just one. It's of type add action, so that tells us what happens if we invoke that operation. In this case, of course, it adds an item to that collection. It also tells us what method we need to use. In this case, it's an HTTP post, and what data the server expects. It's a recipe. And since all those things are URLs, of course, a machine can go and look them up if it doesn't know yet what a recipe is or of what properties a recipe consists of, for example. So that really allows you to create completely generic API consoles, SDKs, and things like that. And I think one thing which we should mention here is that JSON-LD got really wide adoption already. It's quite new, so it came out in January. But there are really a lot of projects, a lot of companies which use it already. For example, Google, as I told you before, Microsoft, Digital Public Library of America, for example, GovUK, or the BBC. The BBC is actually quite was actually one of the earliest adopters, and it's kind of a pioneer in that linked data space. So, for example, if you go to BBC Music, that's completely powered by linked data in the background. So they really ingest data from Wikipedia, from Music Brains, and all of that is based on linked data. And that way they can really build compelling websites without having to create all that content themselves. So for example, that video, I don't know where it comes from, and there is all the biographies down there. And the same thing has been done for the World Cup, for example. And there, it's quite easy to understand that there is a lot of data. So there are teams, matches, everything is interconnected. There are stories about teams, about matches, and this all ties together. And that way you can really, you model the data and the way it really exists in the real world. And that way you build kind of really compelling user interfaces. You can follow those links and explore the data, just as a user would explore the data or the information on the website. And just before I was uploading this my slides, I saw on Twitter that last night they opened up the linked data platform. So it's called BBC Things, apparently, and now you have access to all the data they have. So you can actually leverage the data they have about, I don't know, I haven't had the chance yet to look at it, at least I mentioned politics, sport, music. I'm quite sure they have quite a bit more there. And the nice thing is, it's already available as JSON-LD. So whenever you build an application which, I don't know, has something to do with music, politics, you can really leverage that data. So you don't have to build up that knowledge base yourself. And it's, of course, quite trivial to integrate it because everything uses the same shared data model, the same shared vocabularies, etc. And I think that's one of the main strengths of linked data. But just to give you kind of a bit of an outlook about what the rest of the semantic web stack has to offer, I would like to mention two things, but this is basically a representation of the semantic web stack. An important thing to mention here is that the semantic web is not a separate web. It's really an extension to the current web. So it's all based on our typical web standards, so URIs, HTTP, etc. On top of that, we have RDF, the data model, as I showed you before. We have serialization formats, such as JSON-LD, RDF XML, you should forget about that, and a couple of others. We have models, the vocabularies, we have rule engines, we have quite a bit of logic, we have a query language, etc. And that's where it kind of starts to get complex quite quickly. And most of those specifications are not easy to read, and there aren't really that many tutorials available. But nevertheless, I would like to show you a bit of it. But keep in mind that in most applications, you don't need all of that. So you really just need a subset of that. So you can keep your MySQL database, your relational database, or you can use a NoSQL database such as MongoDB or whatever. You expose it as JSON-LD, you mark it up, you use Hydra to describe your interfaces, etc. And that's, in most cases, already enough. But if you want to do more, then there exists more. And one thing which is extremely powerful, but that's also quite complex, is reasoning, for example. And that's something which is not used at all in other approaches, I think, or not even supported in that case. And probably the easiest way to explain that is that it allows you to make kind of implicit data explicit. So, for example, if we have a resource and we state it's of type schema.org airline, then we know that, but we don't know much more about that resource if we just get that data. But if RDF reasoner is used and it looks up the vocabulary, then it will find in the definition of schema.org that airline is actually a subclass of an organization. And that way a reasoner can infer for you that Lufthansa is also an organization. And you can do quite fancy things with that. So you can have sub-properties, you can state that two things, even though they use different URLs, are actually the same. So all properties apply to both automatically. All of that can be done at runtime. So if you run a query, it can infer that data for you at runtime, so you don't have to store it, etc. So that's quite powerful. But as I said, in most cases, you don't need that. But if you really want to model your knowledge accurately, then this is a very powerful tool. And the other thing I wanted to mention is SPARQL. That's the kind of standard query language for RDF. And it looks a bit like SQL, but it is a bit different because it doesn't work with tables, such as in a relational database, but with graphs. And the way you query it there is you define a graph pattern. So in this case here, I'll probably draw a bit on that slide. This case here, for example, we are again querying the recipe we got before. So we directly query that website. So we don't do anything else. We just say, you know, the source of the data is that website. And what we want to do is we want to retrieve the name and the calories of that recipe. And the way we do it is we describe the graph pattern, so the shape of the data that we are interested in, and bind certain values to variables. So we state in this example that we have a recipe, we bind it to a variable, but we don't care about it, so we don't return it in a select. It's just something, and that something has a property, a predicate of schema.org name. And the value of that, we bind the value of that to the variable name, and then we return the value here. Similarly, that recipe, that entity, has another property. It's called schema.org nutrition. And the value of it is another entity. So again, it's kind of a structured value. It's that nutritional information that we saw before. And that nutritional information has, again, a property, calories. We bind that to the variable calories and then return it here. If you run that query, and you can try that after the talk, I can show you if you want, it really returns that data. So it's much more powerful than screen scraping, for example. It's much more reliable because you really operate on the data instead of the specific HTML structure that the designer chooses to, you know, visualize it to represent that information. And of course, I mean, that in this case here, what happens is the SPARQL engine goes, downloads that document, extracts the data, and then does the query locally. And that was it's kind of one option, and the other option that existed till now was to do that query remotely. So instead of downloading the data and doing the query locally, you send the query to the server, and the server sends you back just, you know, the result you're interested in. And surprisingly, as it might sound, but that has been really kind of the preferred approach on the semantic web. But I mean, we're all API guys here, I guess. No one would really put a SQL server on the web, right? I mean, you could do that for partners or something, but you wouldn't do that publicly. You wouldn't give anyone access. I mean, it's quite easy to craft a query which brings down your server. And thus, it's not really surprising that most of those SPARQL servers are down half of the time. So we wanted to kind of fix that, because those traditional two options really didn't work if you really want to scale that to the size of the web. And the way we approached that is we introduced something which is kind of in the middle between those two. So we dumped down the server quite a bit. Actually, you can use just a static file server like Apache, for example. And it supports just enough functionality to be able to return an interesting subset of the data. We call it a fragment. And that way, the client doesn't have to download, gigabytes of data, but just a couple of kilobytes, perhaps. It typically downloads a bit more than it's strictly necessary, and then does the rest locally. So it completes the query locally. And that's kind of an engineering trade-off. The server is really dumb, but it's really fast. It's static. You can cache a lot of things, which you can't do at all with if you do the query directly in the server. And you can do extremely sophisticated queries on the client side, which you normally can't do with a normal web API unless you really build the tool specifically for that web API. Now, unfortunately, I'm already almost running out of time. So if you're interested in that, or if you want to see a demo of that, I can show you afterwards. You can also find all the specifications and everything else, a lot of presentations about this on our homepage. It's hydracg.com. CG stands for a community group. It's a W3C community group. So we're trying to standardize that as well. It's completely open, so everyone can join. You don't have to be a W3C member or pay something or anything. Really just go in the site, sign up, create a user account, and click on the join button, and then you're part of it. And actually, I would like to invite you to do that, because only that way we can assure that we are actually building something which works for everyone in the long term. And if you want to learn a bit more about JSON-LD and Hydra, so if you want to see how it really works in kind of a real-world API, I'm giving a second talk in this room here at 3:50, so after the next talk, and that will show you how you can build a simple web API with those two technologies. Okay, that's all from me. I hope I was able to show you that there exist other approaches, that linked data, semantic web, as scary as it might sound, it is really simple. Like, the principles are very simple. Of course, you can do fancy things with it, but you don't have to. Now you have really technologies which are practical. They are kind of very similar to what you already do, but you just give a bit more understanding, a bit more context to a machine, and that way you can really extend what's possible quite a bit. Okay, that's all from me. Thank you very much.
If you could stand at that mic, that would be good.
Sure.
So I'm going to take a few questions here, and I'm going to start off because there's one big question that I think a lot of organizations are going to face. So you did a very good job of communicating the benefit and the value of taking a linked data approach. Simplifies a great number of things. What do you recommend for organizations who currently have all this data, tucked away in, much more structured databases? How do you go from, how do they, bridge the gap to this world? Should they go back to the drawing board and figure out, is there an easier way to structure their data in these old databases in a way that supports a linked data future? And then what do you do if you're a startup and you have greenfield? What do you do there?
Well, there are, of course, several options. I mean, you can either continue to use your database and just expose data in such a format. If you already have a JSON-based web API, in most cases, all you need to do is add a context, so that add context property, and have that mapping there. And that's really enough in most cases. Of course, if you start with a clean slate, you could evaluate the use of triple stores, which are databases that have been created specifically for this data model. But that changes quite a bit of your architecture. But you can also, of course, use things like MongoDB, which work quite well for a lot of use cases. And again, there you just add context, and you're basically set.
So MongoDB is in particular a good, is that a triple store, natively a triple store? Or is
no, MongoDB is a document store, so you just basically put your JSON documents in there, and you know, if you have just read accesses, then you basically just dump that out kind of straight from your store and don't have to do much work there. Yeah, I mean, of course, the kind of full-blown solution is to switch to a triple store where you can use SPARQL, for example, and that gets quickly complex. It's probably not a problem from the complexity point of view, but more that people aren't familiar with it. So people are familiar with things like MySQL, etc., MongoDB perhaps, or other NoSQL stores. And there's no need to really re-architect the whole system. You can just, you know, you map your internals to an external representation to schema.org or whatever, and that way other people can benefit from your data.
Okay, and do that in the API layer.
Exactly.
Yeah. Any other questions? Yeah. Okay. Yep.
Hi, myself have one question. Means I want to know how many people use JSON LD as export data export formats. Means I want to know, is it worth to spend enough time or energy to export your data in JSON LD format, or is it RDF is enough for it, or?
Well,
from your experience?
I don't know how many people do that, but there are quite a few companies and APIs and websites out there that use that. So I showed you before that microdata, that markup of the recipe in HTML. Yeah. People actually find JSON LD easier. So Google, for example, is now starting to support, you know, instead of having that markup in the HTML, you include a script block and just pop a block of JSON LD in there. So for example, if you booked a flight, then your airline probably sent you a confirmation email, and in there is quite likely already a JSON LD block which describes the flight, and Google is then able to show you a nice summary.
And another question means, is there any particular tools available in the market that we can use it straight away to export our data in JSON LD format, so I don't need to do too much work on that side?
There are JSON LD
RDF is a tool called Gina is available where you can write a code and convert your data into RDF XML format. So is there something for
Gina, for example, does support JSON LD natively, so you don't have to do anything there. It supports it out of the box. Okay. There are other tools available. There are processors, JSON LD processors in almost every language already there. You have JavaScript implementations, PHP, Ruby, I don't know, Python, quite a few languages. But really, I think the more complex side is actually not the provider side, because there you really have, in most cases, just to add that context, it adds more complexity on the consumer side. And there you're quite well covered already with those JSON LD libraries.
Thank you.
You're welcome.
Yeah, and one other point I want to add as I'm going over here to this gentleman, you know, at least something that I've learned is I don't know if it was that clearly communicated, you know, because Google and the search engines support it, for those of you who a part of your business is about search engine optimization, this now becomes one of those arrows in your SEO quiver. You know, this is a way to search engine optimize your site. It's just another way. I mean, there's about 8 million techniques to search engine optimize your site, but this is sort of like Google, Microsoft. Those guys are out there saying, hey, if you make your data, make your website much easier for our machines to understand, guess what? You're going to get ranked higher. It's a gimme. I mean, and Google and Microsoft and those guys don't generally give you much. They leave you to figure it all out. But in this case, it's pretty surprising when suddenly sites realize they get that religion, like, wait a minute, this gets me some better rankings if I just structure my data this way. That sometimes is all you need to convince whoever you have to convince to make the investment to make it happen.
All right.
Yeah, so I work for an enterprise, and I have a really big problem trying to get them over the unfamiliarity of obviously RDF, linked data, Hydra, right? I think I personally get it, but it's very hard to get that across to the organization.
Yeah.
And what I'm afraid of is that our organization is instead going to go with the more familiar approaches, like we saw earlier today, like Swagger and Ramel. So that's the problem I have, trying to convince them. And one thing I might ask you maybe is, what do you see are the problems with Swagger and Ramel? Are the problems that enterprises will encounter that they could avoid those problems if they skip ahead, invest the time and effort to learn the things like RDF and linked data?
I think that's really what I tried to convey in the beginning of my talk. So Swagger is kind of, I see Swagger as a cure of the symptoms. So you have a tool which creates that HTML documentation for you with those kind of API consoles embedded in there, but it doesn't actually solve the underlying problem. So it doesn't solve the problem from a system point of view. So it doesn't help you in any regard if we're talking about integration, for example. If you have a consumer of that data, Swagger doesn't help the consumer at all. Of course, it can generate those HTML forms that allow you to test the API, but it doesn't tell you anything about your data. Probably if you have 3 APIs which are about recipes, for example, they all use different things, and Swagger doesn't help you there at all. With this approach, I agree you have a bit more complexity in the beginning, but that pays off in the long term. And as we all know, the future is longer than the past. So,
but theoretically, Swagger and Raml, people behind it, and I'm familiar with who those people are, they can adapt those tools to design LD-driven APIs, right?
Yuri kind of alluded to that,
right.
Saying that they might change their what they call them, their traits to actually. Yeah, I think Yuri, I haven't got a chance to talk to him in detail yet, but he kind of alluded that their traits that they have in Raml might evolve into proper hypermedia. But if he sees that as a better form of trait, if he sees hypermedia as better than traits, why are they pushing traits now? Why don't they just say, well, hold on, hypermedia is a better approach?
Traits is just a term they use because Raml, for example, is mainly a design tool. At least I see it as a design tool, and you have those traits that you reuse, across your designs. But from a consumer's point of view, it's not a trait anymore. It's just part of the API. And from a consumer's point of view, it is hypermedia in that sense. But yeah, I had the same discussion with Yuri. So probably something is going to happen there.
Well, I know that he'd be more than happy to have you join the Raml work group and influence in this direction. They're looking for lots of participants to steer it. Okay, great, yeah. Well, I think also to your point about traits is that, and what Mark is saying is all about reusable patterns, right? So patterns evolve in linked data as well. In fact, they're essentially enforced by schema.org. So right. you can see where there's some opportunity. I think the answer to your question of, well, why don't they just leapfrog and go straight to this is because just like anything, you've got to answer the biggest market need first. And the biggest market need, this is relatively nascent. 20% of the websites support it, true, but it's still relatively nascent in the larger scheme of the API economy. There's still plenty of people going that other direction.
Yeah, I mean, JSON-LD has come out in January, so right. It's not that old. I mean, it obviously takes a bit of time. The tooling has to mature as well, but the adoption it already got is quite stunning, I would say. I mean, I haven't seen a technology so quickly adopted the last couple of years as JSON-LD has been.
So do you find it frustrating, though, to see the success of Swagger and Raml?
So the question was, do you find it, I'm just repeating the question on the microphone so the video picks it up. The question is, do you find it frustrating to see the traction that Swagger and Raml are getting?
No, I mean, Swagger, Raml, I see them as tools that help designers. That doesn't really mean that the API can't be a JSON-LD API, for example. It's just a tool that helps designers of APIs. Raml, for example, has those nice things which allow you to mock APIs. Of course, they could do a bit more to simplify the creation of JSON-LD-based web APIs, but I think it just takes some time to get there. I mean, eventually we will get there.
For example, couldn't they, essentially, couldn't you tell it where to, like schema.org pointed at that, and then it would automatically pull stuff in, autocomplete, where you're building.
Exactly.
You can do things like that. So.
Yeah, this sounds like an earlier discussion I had years ago about, architects in our organization saying we're going to go SOAP, and then maybe this REST thing we'll do later. We'll evolve from SOAP into REST, and that just can't happen, right? Because there's two fundamentally different paradigms.
Right.
But are you suggesting maybe that Raml and Swagger, if you start that today, you could easily migrate to something like Hydra? Do you think there's an easy path? I wouldn't think so. I think you have to model your data with RDF underneath first.
With JSON-LD, actually, it doesn't really matter what's underneath. You kind of annotate it. You can annotate it after the fact as well. So that's something quite unique about JSON-LD, for example.
But that assumes you start with JSON-LD.
No, you don't have to. Even if you have like an arbitrary JSON-based web API, you can enhance that later on with a context and turn it into JSON-LD that way. And that's actually something I will show in my next talk.
Okay.
Brought to you by MuleSoft, provider of the industry-leading Anypoint platform for APIs.